Well, something I want to point out is that normally when it is when congruent triangles are counted as one and not different, they will say that. So if it doesn't say that, you can assume. You should assume that like they're talking about all the triangles, not just the non-congruent ones.
So like if they counted like translations and rotations as the same, you think they would say like uh translations and rotations are the same?
I think they would say that. Although like typically it just like normally like it's just that like we're so used to them always saying it, we just kind of take it for granted, I think. But I think they normally all say that, like when you have rotations, translations, and stuff.
Okay. I mean, I feel like, it still could have specified by saying like um translations and rotations are not kind of known as the same and it has to have positive area, right?
Yeah,
Yeah.
but I think like
Um,
on the positive area one, I think like for this level, like I don't think they expect people to know what positive area even like means, I guess.
even means?
Maybe I'm not sure.
I don't know. Basically, it could have been worded better. Just assume to the best of your ability, or like, just with your experience, I guess. And then just move on, I guess. All right. Okay, next question. What is the numerical value of the product of the lengths of all diagonals of a regular hexagon of side length 1? Okay, the value of the product of the lengths of all diagonals of a regular hexagon on side length 1. Um, Again, I feel like this one also wasn't incredibly specific. So like there's two kind of things that this could mean, right? It could mean that we look at the types of diagonals that this hexagon can have, and then we multiply them together, or we look at like all the diagonals that are like possible in the hexagon, and we multiply all of that together. Um, so again, I feel like this one wasn't what was also a little bit vague, but I would assume that it's talking about, like you draw out all the diagonals and you multiply the lengths of all of them together. And also, if you just did the types of diagonals, you only have two types. But I don't know. Maybe it could have also been possibly asking that. I again feel like I don't know. It's just a little bit vague. But so I would assume that you're taking the product of all possible like diagonals that can be drawn in this in this hexagon. So let's just go ahead and do it like that for now. Um, so again, there's going to be two types of diagonals that we can draw in this regular hexagon. One that goes from opposite vertice to vertice, so like a large diagonal, like a diameter, and also a we also have a smaller diagonal that just jumps to one vertice like this. So let's figure out what these lengths are. So in a regular hexagon, we can draw a bunch of equilateral triangles, right? So um, it has sine length of 1, so all of these are going to be 1. And then we can see easily that this long diagonal is going to have a length of 2. So long is 2. And then let's look at the short one. So a a regular hexagon angle is 120 degrees, right? What we can do is drop down this altitude, and then we have 60 degrees right here. And then because we drop it down perpendicularly, this is going to be 90 degrees. So then we have 30, 60, 90. And then if this is 1, then just by applying 30, 60, 90, we're going to get that this is root 3 over 2. And then this is going to be another root 3 over 2. So then you add those together, then the short side is going to be, or the short diagonal is going to be root 3 of length. You can also probably do this in a lot of other ways, but that's just how I do it. You can do it in other ways too. Okay, I'll just leave that there. Okay, so now we have to see how many long and short diagonals we can draw, and then multiply that many together. So if you draw the long diagonals, you can see you can only fit in 3 long diagonals. So that means we're going to multiply 2 3 times, so we're going to multiply 2 cubed. And then let's see how many short you can draw. You can draw one here, you can draw one here, one here, one here, and one here, and one here. It's like that Star of David thing. But yeah, so we're going to draw 6 short diagonals. So that means we're going to multiply root 3 to the 6th power. Okay, so then this is going to be a product. So then we have 2 cubed times 3 cubed, which is 8 times 27. And you have calculators on target, so no worries there. And then this is just 216. And yeah, that is our answer. So our assumption was also correct. Anything you want to say there, Bill?
Again, like if like in this problem, they never said that diagonals of the same length are considered the same and not like multiply together. So I would like personally,
I mean, it also doesn't say that they're different. It just doesn't specify.
well, I mean, some things you're just implied. Like if it doesn't say that if they're different, you kind of just assume it. I mean, it is saying that all diagonals. So
I mean, but it could mean just like it's saying like lengths of all diagonals. Like I feel like it can also mean just like you're looking at the types of diagonals, and then
well,
you're looking at the lengths of that.
if it's talking about like types of diagonals, I feel like it will be worded as all diagonal length,
All
not length of.
diagonal lengths, not lengths of all diagonals.
Yes, exactly.
Okay, language. Uh, um, sure. Um, yeah. So I mean, then you can just go with that. But I still feel like you know maybe it could have been a little bit more specific, just so like you don't have to be that critical just to find just to know what they're talking about. But anyway, let's just move on. A lattice point is an ordered pair xy where both x and y are integers. A triangle is formed by the 3 points 1 1 9 1 and 9n. For what integer value of n is greater than 0 are there exactly 560 lattice points strictly in the interior of the triangle? Okay, so we have 3 points, 1 1, 9 1, like 9 1, and 9n. So it's somewhere here, but it can be at any height. So we have a triangle here. And then we want this so that there are exactly 560 lattice points strictly in the interior of the triangle. So like it says, lattice points is a point where the ordered pair xy, where x and y are both integers, sorry. And when it says strictly in the interior of the triangle, it means, if you have lattice points that are on the triangle, those aren't counted towards the 560 lattice points. Okay. So yeah, so how are we gonna do this? We want to find like a better way to count lattice points than just like I don't know than just like tackling it kind of raw here. Um, like what you could do is you can make a rectangle that is like this, and then counting lattice points that are inside the rectangle, strictly inside the rectangle, is pretty easy, right? You just like make the sides of your larger rectangle smaller, and then you have a lattice grid, and um you can just count that easily. And then you can look at the triangle lattice points as you take those rectangle lattice points, you take away the points that are on this side, and then you divide it by 2, right? So if you take away the points that are on this side, then you'll just have points that are in here and points that are in here. And then if you just divide that by 2, you'll just get the lattice points that are in there. So that's a fine way to count it. And then you make a formula for that, and you equal it to 516. You solve for that. Another way you can do this is that you can estimate the number of lattice points with area. So like in wait, let me think about this. Like in the area of one in the area of 1 unit, you expect like 1 lattice point to be in it, right? Um, it's a little bit weird. I feel like if you have a 9 by 9, I don't know. So you can kind of estimate if you want to. You can kind of estimate the number of lattice points as the area of this triangle, I would say. So you can find the formula of the area of this triangle, estimate it to be the number of lattice points, and then solve for n. And then you'll get like an approximate value of n, and then you can try near values of n and see like if any of them would get you 560 lattice points. But I mean, still, like to test the ends, you would still have to find like you still have to like I don't know, count it well. So I mean, you still kind of have to use this rectangle diagram. Um, okay, but anyway, so if you do this rectangle diagram way, so like I was saying before, you can make a rectangle of points of lattice points inside of this rectangle, and um, the number of lattice points that are on this side is going to be this side minus 1, and this side is 8. So this is going to be or wait okay, so this is a side of 8 length, which means it's going to have 9 lattice points. 9 lattice points on it, right? Like if you have a side length of 1, you're gonna have 2 lattice points on it. So we're gonna have 9 lattice points. This is a length of 8, and we can see that we're not gonna count this point or this point on the sides. So we're gonna subtract 2 lattice points when we go into the interior of this rectangle. So that means we're gonna subtract 2 from our 9 lattice points on this side, which means that we're gonna have 7 lattice points that are on the interior of this rectangle. And then looking at this, what we did with this was we subtracted 1 to the length of this side, right? And the length of this side is going to be n minus 1. So then the number of vertical lattice points in the interior of this rectangle is going to be n minus 2. Okay, and then So n minus 2 times 7 is going to be the number of lattice points that are in the interior of this rectangle. And we're going to have possibly some points that land on this diagonal. And to our exact formula is going to be this minus that, number of points on diagonal over 2, right? This is going to be the number of lattice points that are within the triangle. Since we're not going to count these on the triangle, so we have to subtract them, and then we just have like these two sides, and then by symmetry we can divide it by 2, and then we know that this has to equal 560. But since this is math counts and time is a big factor, we want to try to do this as quickly as possible. And I mean, you can kind of see like approximately there's not going to be not like usually not a lot of points that are landing, if any, on this diagonal, right? Since in the interior of this, we only have 7 possible points that are on this horizontal, right? So there are only at a maximum of 7 points that can all land on this diagonal, right? And that's only if this has a slope of exactly 1. And if it does not have a slope of 1, then it's going to go through much less points, right? So for now, we can assume, let's just assume that this number of points is 0 to make our calculations easier, and then we can estimate a value of n. And then with this estimate of n, then we can go, look into the specifics and see if this n works or not. And if it doesn't, like if there are too many or too few, then we go up or down to find the actual value of n. But we can do this to quicken our search. And there's also like not like a really good formula to like capture the number of points that are going to land on this diagonal as a function of n. So we're just going to estimate n for now, and this will be faster than if we got a formula for the number of points on it and stuff. So if we estimate this to be 0 and we solve for n, then we get n is approximately 162. So we want to try n's that are around this and see if we can get 560 lattice points. And when you put that into the calculator, you get that n is exactly equal to 162. Like you get 162.00000, which means that if we test n equals 162, and if we get that the number of points on this diagonal is actually 0, then 162 is going to be our answer, right? Since we assumed that this number of points was 0 in the beginning. So right now we can test n equals 162, and if 0 points land on this diagonal, then 162 is going to be our answer. So let's test it. So how are you going to test if lattice points land on this diagonal? Well, the easiest way to do it would be to look at the slope of the diagonal. So the diagonal goes from 0.11 to 162. That's what we're looking at. So then the slope of this diagonal is going to be 161 over 8. So every 8 units that it goes, it's going to go up by 161. Now, for the diagonal to land on a lattice point, it has to land on an integer point. And it's just not possible with this slope, right? No matter how much you go, so if I go 4, no matter how much I go as my x, my up y value will always be a fraction, a non-integer value, unless I go 8 on my x. so then that means, we're not going to hit any integers on this diagonal. So, if we don't hit any integers on this diagonal, we're not going to hit any lattice points. And like I said before, if we saw that 162 lands on 0 lattice points, then this will be our answer. So then n equals 162 is just our answer. And yeah, we can see that 162 is our answer. Anything you want to say there, Bill?
Uh, uh, we also thought about doing this problem with area. I guess you could try that. I wouldn't recommend it exactly, but it's something you could try, I guess.
I think that's kind of janky.
Yeah.
Do you estimate do you estimate 1 unit area to contain 1 lattice point? I mean, it's not. I feel like it's not a great
Yeah,
estimation, right?
it wouldn't be a great estimation, I think.
Um, we can look at a 9 by 9 square, and then so the number of lattice points inside is going to be 64, right? And the area is 81. So not the best approximation. But if you can only think of that on the test, then you can try and go with that. Okay. Next problem. The positive integers 1 through 49 are divided into k disjoint subsets so that no two integers whose sum is divisible by 10 are in the same subset. For example, 13 and 37 cannot be in the same subset. What is the smallest value of k? Okay, we're looking at we're dividing these integers into subsets. No two numbers in the same subset can have a sum that is divisible by 10. So we're seeing that it can't divide by 10. So it's telling us that we should look at the mod of the numbers. And that's all we have to look at, right? Because our only restriction really is that the sum cannot be divisible by 10 of two integers that are in the same subset. So yeah, so we're just gonna look at the mods of the numbers. So our digits, we're gonna have 1, 2, 3 all the way to 9 mod 10, right? 9 mod 10, and then these are our first 9 digits, and then as we go, we're gonna have 0 at the beginning of our mod 10. So on the 10 through 19, we're gonna have 0, 1, 2, 3 all the way to 9 mod 10. And then on the 20 through 29, we're gonna have 0, 1, 2, 3 dot 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 all the way to 9 mod 10. And then so on 30 through 39, we're gonna have the same mod 10. And then 40 to 49, we're also gonna have the same mod 10. So if we're looking at the mod 10s of everything, we're gonna have 5 of everything except 0. We're gonna have 4 0 mod 10s, but 5 of everything else. Okay. And now let's look at our restriction. So we want to put stuff into subsets, and we can't have two integers in the same subset whose sum is divisible by 10. So that means we can't have two integers whose sum of mods add up to 10. So like they're mod complements, right? So one can't be with 9, 2 can't be with 8. 5 can't be with 5, and 0 can't be with 0. So we're just going to sort it by this, and we want to put as many numbers as we can into the same subset, because we want the smallest possible number of subsets that we can have. So what we can do is we can put all 1s, 2s, 3s, and 4s in the same subset, right? like all of them, all all of these, because each of these complements are not in the same set, right? We're just keeping all of this in the set, and like none of these are complements of each other. So we have all 5 of 1, 2, 3, and 4 in the same subset. None of them, none of these sums of 2 will be divisible by 10. And we can also do the same thing with 6, 7, 8, and 9. If we have this, then none of their complements are in here. So we also can combine any of these to a sum that is divisible by 10. But we can't have like all 5s or all 0s in here, right? Because if we had all 5 5s or all 5 0s, they can combine with each other, and then that would be divisible by 10 because they're complements of each other. However, we can have just one 5 that is in here, right? Because if we just have one 5, then it's not going to have a complement of itself to be with. So then, then this whole set is still not, you still can't have any pair that's sum is divisible by 10. So we can include one copy of 5 and 0 in each of these sets, right? So one copy of 5, one copy of 0. And I'll put like oops. I'll say like I don't know, 5 times 1. That's just one copy of 5. So you can have one copy of 5 and 0 in each of these, because to combine with itself, it has to have 2 of itself, right? And then we're gonna have 3 5s left and 2 0s left after we put this arrangement. And now you're just gonna have to have each of these 5s in a different subset, right? If you have 2 of them in a subset, then they can combine and have a sum that is 10 or divisible by 10. So you have to have each of these 5s in a different subset. So that means we have to make 3 more subsets for the 5s. And the 0s can just hitch a ride on any of these 5 subsets, and this is fine. There are enough of these for the 0s. So basically, we're going to have to make 3 more of these subsets so that the 5 are alone. And then we have the 2 from before where we dump like all the other integers in. And then we can't have this any better, right? The minimum possible, we can see that it has to be 5, right? Because we have 5 5s and none of them can be together. So we have to have at least 5 subsets. And we found a combination that has 5 subsets. So then this must be our answer. K must equal 5. And the answer is 5. Okay, anything you want to say there, Bill?
No. Yeah. This.
Oh,
Yeah.
all right. Okay, last problem on target. 3 real numbers are chosen at random between 0 and 1. Oh, this problem. Oh gosh. Okay. What is the probability that their sum is no more than 1? Express your answer as a common fraction. Okay. This problem, our solution, or we spent quite a long time, me and Bill, on this problem. We did come up with a solution, but it was a little bit long. There could be there's probably a better solution
There
than
definitely
ours.
is a better solution.
Definitely.
I mean, I don't think they're gonna expect you to like use the
It's
stuff that we did.
okay. Probably, I guess. Um, sure. Yeah. We'll show you our solution, but it's there's probably a better solution out there. But this was the best we can think of, I guess. Okay. So first, first I'm gonna make like a what is it called? Um like it's a smaller thing of like your proof that you go off of in your bigger proof. What is that called? Axiom?
I don't know. I haven't written proofs in a while. I don't know.
There's like a name for it.
I don't remember.
Or was it corollary?
I've never even heard of that word. I've heard of axiom, but never like code. What?
Corollary.
Yeah, I've never heard of it.
Okay, well, oh, a postulate?
Postulate. Yeah.
Postulate? Uh, statement. A postulate is a statement, also known as an axiom, which is taken to be true without proof. Oh wait, lemmas. I think it's lemmas. Lemma, yeah, lemma is a short theorem used in proving a larger theorem. Yeah, it's called lemma. No, okay, so postulates and axioms are like trivial. So like I don't know. But yeah, lemmas are like smaller proofs. Okay, so let me talk about this lemma first. Okay, so um, first, if we're taking two real numbers, um, two reals between 0 and 1, the probability that their sum is less than 1 or is less than 1, you can easily see that that probability is going to be 1/2, right? Because just by symmetry, right? Um, you know, each of the reals is symmetrical about 0.5. So the sum of the two reals has to be symmetrical about 1. So if it's symmetrical, if the sum of the two reals is symmetrical about 1, then the probability that the sum of the two reals picked between 0 and 1 is going to be 1/2. Now, my lemma is that if we're looking at two reals between 0 and 1, the probability that their sum is less than some real p is going to be p squared over 2. Now here's my proof. So um, so we have two reals. They're being picked between 0 and 1, and um, the probability that or okay, p. Let me specify first. P is going to be a real number that is between 0 and 1. Now, the probability that one of these real numbers is between 0 and p is going to be p, right? The probability that like the first number that we choose, probability that it's between 0 and 1/2 is going to be 1/2, right? It's just that's just the length of the interval divided by the length of the total possible interval. So the probability that one of these numbers is going to be between 0 and p is just going to be p. The probability that the other one is also going to be between 0 and p is also going to be p. So the probability that both of them are going to be between 0 and p is p squared. Now, if we're given that both of them are between 0 and p, we're looking for the probability that it's less than p, then this is just going to be 1/2, right? It's like the same thing that we looked at before. If two reals we're choosing it between 0 and 1, probability that it's less than 1 is just going to be 1/2. Why? It's again because of symmetry, right? Each of these reals is going to be symmetrically distributed about p over 2. So the sum of the two reals are going to be symmetrically distributed about p. So if we're looking, if we're given this and we're looking for that the sum is less than p, then it has to be 1/2. And then the probability that both of these were going to be in this range was p squared, right? So that means the probability that the sum of two reals between 0 and 1 and it is less than p is going to be p squared times 1/2, or p squared over 2. Okay, that is my lemma to prove my prove the larger problem, which is this problem. Okay. Now, now what we're basically going to do is we're going to so we're choosing three numbers in our scenario here, and our first number, we're going to look at it where we're choosing between 0 and 1, and depending on what we choose, it's going to give a different probability for our other two numbers off of this lemma, right? So like, let's say our first number, let's say it was randomly picked to be 1/2. That means the sum of our last two numbers will have to be 1/2. And these two numbers are chosen between 0 and 1, right? So by my lemma, the probability of this occurring is going to be 1/2 squared over 2. And let's say our first number was 0, then the sum of this is going to be has to be 1, right? So that 0 plus 1 is 1. So then by my lemma, then the probability is going to be 1 squared over 2. So then you can see that if we have our first number, if whatever our first number is, if we call that x, then what our sum of our two numbers has to be is 1 minus x. And then by my lemma, then the probability of this occurring is going to be 1 minus x squared over 2. Since 1 minus x, that's a probability. We're looking at we're looking at that the sum of these two numbers has to be less than this sum, 1 minus x. So then we plug it into the formula that we got before. So then this is saying, if we choose our first number to be random between 0 and 1, and we call that x, then the probability of everything else working out is going to be 1 minus x squared over 2. Okay. But now what? Now what we can do is we can integrate this function. We can integrate this function within these bounds and divide it by our interval length, and that will give us like our average probability, right? We want the average probability of this function, right? That will give us our probability. Well, like our probability is just our average probability, right? So we want to look at the average probability of this. And in calculus, if you have a function, if you have a function f of x and you're looking for its average value over an open interval or closed, it doesn't matter, right? Let's just say generically a to b. If we're looking at the average value of f of x from a to b, then it's just going to be the integral from a to b of f of x dx over the interval length, which is b minus a. So in our case, we want to look at the average value of this function, right? This is our probability function. We want to look at the average probability. We want to look at the average value of this function of in 0 to 1, right? That's where our x can be. That's our interval of possible x. So this is our f of x, and our a and b are 0 and 1, right? So then our average value is going to be the integral from 0 to 1 of 1 minus x squared over 2 dx over b minus a, which is 1 minus 0, which is just 1. So we can just ignore that. So now we're just going to have the integral from 1 to 0 of this function. So first want to integrate this function, and then we want to do the definite integral of it. So if we expand the top, we're going to have 1 minus 2x plus x squared over 2, and then we have everything else. And then just putting the 2 there, we're going to have 1 half x squared minus x plus 1 half dx, and we're integrating it from 0 to 1. Okay, now we're going to integrate it. You kind of have to know a bit of calculus to do this. So this is why our solution is not the best solution, because the intended solution, I mean, they probably don't expect math counts kids, to know calculus. So there's probably a better solution out there, but we couldn't find it. But yeah. Okay, so if we're integrating this, we can just use the power rule or the anti-power rule on each of these terms, right? So, we're going to add 1 to each of these x exponents, and then we're going to divide also by that number. So on 1 half x squared, on 1 half x squared, we're going to add 1 to the exponent, so it's going to become x cubed. Then we're going to divide by this number. So we're going to divide by 3, so then our coefficient is 1/6. So if we do that on all the terms, we're going to have 1/6 x cubed minus 1 half x squared, 1 half x squared, plus 1 half x plus c. And we're looking at it on the bounds of 0 to 1. Okay, and then we just do these bounds. It's going to be, we're going to plug in 1 to this. We're going to get that value, and we're going to minus the value that if we plug in 0 to all of this, right? So if we plug in 1 to all of this, we're going to have 1/6 minus 1 half plus 1 half. Then we need a minus 0 plugged into all of this, which is just going to be 0, right? All these terms have x. So then our average probability, we get it equal to 1/6. And our average probability is just going to be our probability, right? So this is going to be our answer. And if you look at the answer sheet, this is the correct answer. Okay. Anything you want to say there, Bill?
Uh, I guess probably not the best solution.
Well, you just said it wasn't.
Yeah, definitely not the best solution.
Okay.
Hmm,
Yeah.
I'm not sure how you would do this.
Yeah. We were thinking that there might be like a better like geometrical way to think of it, and then it's like really simple. But I don't know. We couldn't think of that. Um. Yeah. If you guys think of a better solution, you can let us know. But I don't know. This is just the best that we got to, I guess. Okay. Um. Bill, you want to do the team ones now?
Oh, yeah, that's fine. Um,
Yeah, I'll send you the problems,
yeah, okay.
or I can just send you a general link I use.
Okay.
Okay, so on it you'll see like here, I can also send it in the chat here. I think I sent it before, but um Here you can find years from 2017 to 2000, and there's like school, chapter, state, and national on each of them. And then under them you have like sprint, target, team, answers, results, and highlights and stuff. So you can just go on any one of them and get the PDF or whatever.
This was nationals, right?
Yeah, Nationals 2012
Okay.
team. So like it has solutions for school, chapter, and state, but not school, or sometimes school, but not nationals for
Okay.
some reason.
I am struggling. Hang on.
There's also
Mhm.
countdown rounds at the bottom. A lot of years. We could have just used that
No. Okay.
for
Okay. You wanna? Okay. So. Oh no. The nth term of the sequence 6, 14, 24, 36 is of the form a(n) squared plus bn plus c for some constant a, b, and c. What is the 100th term of the sequence? So to solve this problem, you would basically plug each one of these in. So like find three of these values and then put them into the equation, like set the equation equal to them. So for n equals 1, it equals 6. So you end up with a plus b plus c equals 6. Right. And for n equals 2, the n squared will be 4, so we end up with 4a plus 2b plus c equals 14. And then for n equals 3, we get 9a plus 3b plus c equals 24. And because we have calculators, we can just solve this. If you don't have calculators, you can hand solve this, I guess. But we do have calculators. So we plug this in and we get so on the Inspire this is menu 372. I just that's menu algebra, solve system equations, and then solve system linear equations. And we end up with a equals 1, b equals 5, and c equals 0. So we put this back in the equation, and we put 100. We set n equal to 100, and we get 100,000. No, 10,000 plus 500 plus 0 equals 10,500. And yeah, that's our answer for number 1. So for number 2, Sarah tossed a fair coin 5 times and Caleb tossed a fair coin 3 times. There were 5 heads and 3 tails in 8 tosses. What is the probability that either Sarah or Caleb toss exactly 3 heads? Express your answer as a common fraction. Okay, so wait, Austin, how did you do this? Because
no.
I never actually got the answer on this one. How did you do this?
Okay. Just look at your cases. So,
Hmm.
first look at like either if Sarah or Caleb gets the three exactly three heads. So if Sarah gets exactly three heads, then Caleb will have exactly two heads, right?
Right, yes.
Or then Sarah's so the combinations of that happening is going to be five choose three on Sarah and three choose two on Caleb, right?
3 choose 2, right.
Right. And then the other case,
And then this
you're gonna have
over 2 to the 8.
no. It's gonna be over eight choose five, right? We're only looking at if they already tossed and got five heads and three tails.
Oh, okay, that makes sense. Okay.
Yeah. And then but you have to add the other case on top, which
Oh,
is
okay, so it
if Caleb got three and if Sarah got two, which would then just be five choose two.
okay, so the thing about this problem is that it already states that there were 5 heads and 3 tails. So it's asking for the probability that if it already has 5 heads and 3 tails, the probability that either Sarah or Caleb tosses exactly 3 heads. Okay. So I guess we just solve this now. So it'll be 5 2 times 3 over, and then 8 choose 3, so 8 times 7 plus 5 times 2 over 8 times 7. You get 40 over 56, 557. You check, that's our answer, 2. 2. And yeah, that's as far as we got, so now we're just going to wing it. In trapezoid ABCD, segments AD and BC are parallel, and measure of ABC equals 90 degrees. A circle is inscribed in the trapezoid so that it is tangent to each side. The point of tangency E divides segment DC as shown, such that DC equals 4 and EC equals 16. In square units, what is the area of ABCD? Okay.
Okay. Well, first you can use the tangents and like get the lengths of the other tangents, right? You know.
Okay. Yeah, so this is 90. This is 90. Tangent each side. So these are equal. So D equals 4. So from here to here also equals 4. EC equals 16. So this equals 16. Square units.
Yeah.
Okay. And these four sides will be equal to each other, right? These will
Yeah.
be equal to each other. Okay. So we're looking for the area of ABCD. Okay. So we know if we drop a vertical from here to here, like this, we know this is 4. So we know this part is 12, right?
Oh yeah. And
This
then
is
you
12,
just
this
get
is
that, and
14, and we can
then
find the height of this, right? So we do. So it's 4. Is this a special triangle? No, it's not.
and then the lengths, the
Wait,
length
this
of
is
those
4
things are
too.
just
This is 4. So this is ends up being
yeah.
20,
That's
12. So this
12
is
and
16.
20. 3, 4, 5.
This is 16. So each one of these is
Yeah.
8, 8, 8.
Yeah. And then you just do trapezoid.
Yeah, just do trapezoid. So it's 12 plus. This 4 is here. So this 16 actually encompasses all this. So 8 plus 16 is 24 over 2 times 16. And this is 36. 18 times 16, which is 288. 288. Yay, that's our answer. Okay, number 4. For a certain sequence, the nth term is the number that gives the same result when added to n plus 1 over n, or multiplied by n plus 1 over n. What is the 2012 terms of this sequence? The nth term is this number that gives the same result when added to n.
Um,
Hmm.
like when n is added to or
What?
multiplied by that.
I'm not quite
What?
sure either.
I think that's what it's saying. So then,
Oh no, I think I got it. It's like an plus n plus 1 over n. Oh, hang on. An
yeah,
plus n plus 1 over n equal to an times n plus 1 over n.
that doesn't look very nice.
Okay, so
Oh well, you can
the
wait. You
thing
can
is
add.
this really even a sequence? Like you're just like the numbers don't really have any correlation to each other. You're just more like we can just look for 2012, I guess. We're just looking for an just that. We're just looking just looking for x such that x plus
Well, there's
2013,
probably gonna be
2012
wait.
equals 2013x over 2012. Do you think that's what it's trying to say?
Yeah, wait, but if there's only one solution for x, then it has to be that, right?
Right.
And you get what 2013 for that? Is that the answer?
Uh,
Oh wow, that's the answer.
yep, that's the answer. 4.
Okay, so yeah, just pretty easy, I guess.
Okay, number 5. Using 4 distinct positive integers, we find the 5 distinct sums of the 6 possible pairs of these integers to be 27, 41, 44, 47, 61. One of these sums occurs twice. What is the smallest of the 4 integers? Okay. Mm, what do you think, Austin? So,
Um, five distinct sums of the six possible pairs of these integers?
yes.
Well, what is that really saying?
Two of them sum to there's 2 pairs that sum to the same thing. So like we have A B C D, A B C D. A plus B equals the same thing, and C plus D will end up equaling the same thing. So I think
Wait, what?
something to
Wait,
notice
I
here
am
is
confused.
maybe
What?
there's 4 odd numbers and 1 even number. Do you think that's going to be important?
I am confused. What? What is it saying?
It's saying that like, there's 6 ways to pair 4 numbers, right? There's 6 ways to find 2 numbers out of 4 numbers, right? Like 4 choose 2.
Yeah,
Wait, is 4
and
choose
you
2?
find the sums.
Yeah.
Oh, you find the sum of the pairs.
Yes.
Wait, aren't there six pairs though?
Yes. One of
Wait, so
these
how do you have
sums
five
occurs
sums?
twice.
Oh, okay, I get it.
Okay. Do you think we should try to find which one occurs twice first?
Wait, let me think. Oh, it says one of these sums occurs twice.
Yeah.
Okay.
So we can list them descending to ascending A, B, C, D, right? We can name the list
Sure.
from
Or
A.
you can or if you don't have them ascending, you can just without lots of generality assign them
Yeah.
and
So
then
we
try
can
to
do A plus B equals 27. A plus C equals 41, right?
yeah, that should be
C plus D
fine.
equals 61. These are like for sure, right?
Or wait, no, I don't think you can have that if like if you have them as ascending, I don't think you can say like
A plus C?
um no, A plus C would have to be 41, right?
Yeah.
But then you don't know what the middle stuff is. I was saying
Yeah,
like
that's
that they're not increasing. I feel like increasing wouldn't help us that much either. I don't
well,
know.
okay, so we know that B plus D is greater than A plus C, right?
Wait, what?
We know that B plus D is greater than A plus C. Actually, yeah. B plus D is greater than B plus C, right?
Yeah.
So BD has to be 47, right?
How do you know not any of these are the one that is repeating though? And
Well,
you don't know which one is repeating
the one
either.
repeating will be A plus D repeats as like B plus C, right? There's, right? Because how else are you going to get something else to repeat? There's no other way for
Mm.
to find two
Well,
pairs that
what if
can
two
be
numbers? What if two
dis
numbers are equal?
distinct.
It's, huh?
They're distinct. So,
Oh. Oh, okay. Yeah, then A plus D would have to equal B plus C.
yeah.
Wait, so then A plus D would have to be 44?
Yeah. So you can solve this now
Hmm.
or like do whatever you want with it.
Yeah, now you can add them all up.
Yeah. You don't even really need all six of these equations, right? It's only four variables. You only really should need four equations.
Okay, you get A plus B plus C plus D is 66. So then um I mean wait, what? I mean you can just put any of the four into your TI.
Right.
That should
Yeah,
work.
that's literally what I'm doing right now.
Okay.
Yeah. And you can solve it and I total. Okay, and I did that. I used this, and this. And I ended up with A equals 12, B equals 15, C equals 29, D equals 32. Ah, technology.
Is that the
So
answer?
12, we're looking for the smallest of the four integers.
Oh yeah, that is the answer.
That is the answer, yep.
Woohoo.
The sum of the first six positive odd integers is 36, which is a factor of 6 factorial. However, the sum of the first five positive odd integers is 25, which is not a factor of 5 factorial. How many integers n greater than 50 less than 99 is the sum of the first n positive odd integers a factor of n factorial?
Wait, it should just be n squared, right? It's just the
Huh?
sum. The sum of the first n odd integers is just n squared. Right?
Is it?
I mean, yeah. Well,
Well,
you can just apply arithmetic series. So if you have n odd integers,
uh-huh.
um, the nth
Oh yeah, you're
the
right.
the nth odd integer will be 2n minus 1. Oh, 2n minus 1. Yeah, it'll be 2n minus 1. And then you take the average of that and 1, which is 2n divided by 2 times n. But that's n squared. Um,
Yeah, it just ends up being n squared, so.
so then we're looking n factorial has to be divided by n squared.
N factorial, oh, no, n squared has to be a factor of n factorial.
Yeah, yeah. Hmm.
How do we go about doing that?
Well, if n is prime,
Well, if n
it's
is
not going to
prime,
work.
definitely not going to happen.
Well, what if n is not prime? If n is not prime, its prime factors has to have listed before in the factorial,
That's true, yes.
and then it's just gonna,
Right,
cancel.
all of its factors would have been listed before, right?
Yeah.
Okay,
So
so
then
basically just
n squared is
non-prime
yeah, just
numbers from 50 to 99 inclusive.
yeah, or it's easier to count the prime numbers, obviously.
Okay, yeah, prime numbers, which are, I don't know my prime numbers. 53.
50. Oh,
51 is
yeah,
divisible by
53.
3. Well,
Yeah,
off to
no,
a
okay.
great start, Austin.
No, I would have. I noticed immediately after. Okay,
Okay,
57 is not.
yeah.
59 is good. 61 is not good. No, 61 is fine. Not 63. 67 is fine. 71 is fine. 73 is fine. 79 is fine. 83 is fine. 87 is not fine. 89 is fine. 91 is not fine.
91 is not fine? What is it?
91 is 7. 91 is 7. 70, 21. It's 7, 13.
Oh, way to throw the
90,
two prime. I didn't consider Abby.
93 is not fine.
93 is not fine. 97?
97 is
Yep.
fine.
So 1, 2, 3, 4,
Okay.
5, 6, 7, 8, 9, 10. 10 numbers. So 50 to 99. That's 50 to 99
Pretty
inclusive. That's 50 numbers.
inclusive.
So it's 40.
Yeah.
Yay. That's the answer. 40 integers.
Oh, too good.
Number 7. The number 2564, 64 to 25 equals n squared.
Okay, first,
What is the
they can
sum
keep
of the
reading.
digits of n?
Okay, so first make like 5 squared and
Yeah,
8, or I
5,
mean 2.
128, and then 2. This is 2 to the what? 6? 2, 6,
Yeah,
okay.
6.
Okay, yeah, 2 6. So
Yeah, and
6,
then yeah,
150.
yeah. Okay, and then divide by 2.
Right, divide by 2. So n ends up equaling 564 z
Okay,
75.
and then just sum of the digits. That's fine.
Yeah, and this becomes
Um,
1064 2 to
5 is
the
always going to be 5, right?
what?
Like 5 to the 64, like
Yeah,
5 to whatever power, it's going to have a digits or units digit of, oh, sum of the digits. Okay.
it's going to be 10 to the
Um,
64 times 2 to the 11. So this is all 0, so we don't care about that. We only care about the 2 to the 11.
ah.
What is 2 to the 11?
Okay, 2 to 10 is 1 and 2, 4. So then 2, 4, 8. So then 14.
2048.
2048.
So that's 14. Would you look at that? That's your answer.
Hmm, not bad.
Number 8. Quadrilateral ABCD is inscribed in a circle radius 6 centimeters. AB equals 80 and BC equals CD. If the area of the quadrilateral is 60 centimeters squared, what is its perimeter in centimeters? Express your answer in simplest radical form. So we have a circle. That's a good circle. That's also a good circle. Radius 6, so 6. ABCD. Okay. Wait. Oh, okay. Sort of like this. A, nope. A, B, C, D. Yep. The area for, oh, if this area is 60, then what is this perimeter in centimeters? So this is a kite. So to find the area, we take these, we multiply them. Um, we take these, we multiply them. Austin, how do you think we should
Okay,
do this?
okay, yeah. So the diagonals, you multiply both them and divide by 2, right?
Yeah, to get 60.
Like AB over 2.
Yeah.
Okay, one of the what diagonals has to be a diameter, right?
Why?
Because so like the other is gonna be a chord, and like the
That's
thing is
true. Yeah.
perpendicular. And if you have
Yeah.
something perpendicular to a chord, it's gonna be a
Yeah,
diameter.
perpendicular and cutting through it.
Or yeah, also bisecting it.
Yeah, bisecting it. It's perpendicular bisector of a chord. That will always go through a diameter.
Yeah, so it's gonna be 6 times the other diagonal. So the other diagonal is 10.
Well, it will be 10 times the other diagonal, right?
Huh?
Wait, I'm sorry. Yeah, the other diagonal will be 10.
Okay, so it's 10 and 12.
Yeah, 10 and 12.
So then
So
do
5,
you just
5.
wait, 5, 5, and then what?
Did you know there's this thing called power of a point? It's amazing.
Oh, oh, that's crazy. Okay,
I
yeah.
think
So
that's
make
how
a
it
make an
works.
equation for that, and then um, well, you have a calculator, so maybe just solve by hand, and then it should be fine. Then you just use Python.
Actually, I'm just gonna do this. Hang on. This is gonna give me a easier number to work with. We're not gonna do this. We're gonna do x 12 minus x. This did not give me an easier number to work with. X equals. This doesn't go in, does it? Can't just factor this.
Doesn't look like that.
Oh no.
Just you have a calculator.
Struggling. Okay. It equals square root of 11 plus 6. Exactly what I would have got if I just stuck with 6 plus x, 6 minus x. Square root of 11. Actually, no. Plus 6. 6 minus square root of 11. So now we do Pythag. Fun.
Fun.
Square root of 11 plus 6 let me do this real quick. Ooh. Okay, yeah. Squared plus 25
Wait, do you get double radical?
What?
Um,
I don't know, man. These numbers seem kind of suspicious.
Suspicious.
It's just a hunch. Square root of 66 minus square root of 6. So you end up with...
You got root 60 plus root 6?
So these two sides, then you multiply this by 2. 2 square root of... Yeah. End up with... And then multiply by 2 for the other side. So you end up with 4 square root of 66. Wow, that's the answer.
Wait, what?
What?
Wait, when I square it... Wait, what is your CB side?
CB, 60 square root of 66 plus square root of 6.
Wait, so it's 6 plus root 11 squared plus 25, right?
Yeah.
Yeah, and then I got 12 root 11.
Did
Oh,
you
well, you had to
square root
square...
that? See?
How is there not a double square root? I guess it just works out.
The other one's square root of 66 minus square root of 6. So the square root of 6 just cancels out.
Okay, that's going to be it for this math meeting. With a few problems of a team left, we'll continue from this next week, and we'll continue with 2011, unless you guys want us to do a different year, and then we'll probably do that year. Okay, well, that's it. Thanks for coming, and goodbye.